Good morning. I hope you had a good weekend and a good Pi Day yesterday. Very important. Posted a little funny, I think it's funny, on our Moodle page. Even though we didn't have class yesterday, it was Pi Day. So that's one holiday. Well, it's not a holiday. We take seriously. Okay, so let's see here. So you did your quiz and it's looking good. I haven't marked that brief little written interpretation that you did, but I'll do that. But great job. And so 2 quizzes done, 2 to go. Oh man, right? We're going to pick up the pace. So we're going to have a chapter 6 quiz and then a chapter 7 quiz. And so they'll be more focused on these chapters because we cover a lot of ground. All right, so we're going to start chapter 6 today, and most of it we have already seen. And so chapter 6, now I'm drawing a blank. It's probably inference for categorical data, which is what we're doing, but I can't remember exactly what it's called. So let me just look it up here. Nope. Inference for categorical data, if you can believe that. It's more obvious to me, I guess, than to you. Inference for categorical data. So just for a little bit of an overview of what's going to happen, 6.1 is basically a review of chapter 5. So we use the ideas of 6.1, which is 1, sample proportion. Now I can't remember if this is what they're called exactly because I closed it. That was silly of me. Okay, inference for a single proportion, but usually I just call it 1 sample proportion. And so it's called inference for a single proportion. Oops, said single, but wrote simple, weird. Single proportion is what the section is called. We saw most of this covered in chapter 5, right? We used it to introduce these ideas of confidence intervals and hypothesis testing. So for that reason, I'm going to use this section to introduce kind of a fun calculation where we can calculate the sample size that we would need for a study. So you can see how that would be beneficial. Hopefully. And then we'll start again in 6.2 with confidence intervals and hypothesis testing. So we're going to use this, we will use this section to introduce sample size calculations. We only do this in this one section. In this one section. So that means you can only do a sample size calculation, or we will only be able to do a sample size calculation in a 1 sample proportion scenario. Okay? But that's okay. That's going to be fine. 6.2 is the difference of 2 proportions. Yeah. Which I'll call 2 sample proportions, but that's basically what it's called anyways, so I'll leave that. This is where, so next day we're going to start, and I'm guessing it's going to take us all week. So difference of two proportions. Now we have two samples and we want to compare the two proportions, right? It's all in the name, but when you first hear it, it's not that obvious. 6.3 and 6.4, we're going to introduce next week, I'm thinking. And in 6.3, we are going to be testing for goodness of fit. Using what we call a chi-squared. So here we have two proportions, and here we have more than two proportions. So we're going to have tools for dealing with one proportion, right? So that's what we've already seen. Comparing two proportions, so I have two sample proportions, or if I have multiple proportions, right? From the same sample, I have categorical data. It's not that crazy to think that if we record hair color, we're going to have more than two proportions, right? We have more than two different hair colors, or although we could break it down into two, but usually we're interested in more. So then we're going to use the chi-squared method, but I'm leaving that until next week. But then we're also going to be able to test for independence in two-way tables. So testing for independence in two-way tables. In two-way tables. So what this means is that we'll be able to consider more than one categorical variable. In fact, two, I should have said two. So two categorical variables with any number of groups. So comparing two categorical variables with any number of proportions each. So we're just going to kind of scale it up and look at and just kind of blossom out and look at, we'll start with one sample proportion, which we've already seen, and then two proportions is the most common one that you're going to consider for most things that you're going to encounter in life, and especially if you're in the biology section, then that's usually what you're going to be doing. And then if we have more than two proportions, what can we do? We can use the chi-squared. And then what if I have two categorical variables? Then I can make a two-way table like this, and I can compare the proportions for independence is what we're going to focus on. Okay. So in 6.1, it was called Inference for a single proportion. And maybe what I'll do is I'll do this. I'll do 6.1. This is today. 6.2 is going to be Thursday and Friday this week. And then 6.3 and 6.4 is on Tuesday and Thursday. And then, oh my gosh, we're going to have our third quiz, right? So picking up quick here. I had forgotten, so I'm going to bump this down. Well, I hadn't forgotten. I just didn't think it would happen so soon. Okay. And then on the Friday, quiz number 3 on chapter 6. Okay. Too soon. No, we've got time, right? 2-week intervals. Okay. So inference for a single proportion. Let's just do a recap. I know this is probably a little bit boring, maybe, but it's nice to have kind of a one sheet that you can refer back to, right? So I just want to talk about, well, what are some of the conditions? And then from here on out, when I say hypothesis testing, I'm going to mean hypothesis testing using the p-value approach. Okay, so just as a little note here, from here, or maybe going forward, when I say hypothesis testing, I mean using the formal p-value approach. I mean using the formal p-value approach. Okay, you're still expected to understand the link between a confidence interval and the p-value approach, right? And you should be able to kind of answer questions in terms of the confidence interval, right? But when I say do a hypothesis test, I mean use the formal p-value approach. Okay, so sorry, I just need to go blow my nose real quick. I'll be right back. Put it on mute, otherwise it's rude. Okay, sorry. Better, I can breathe, weird. Okay, so I'm gonna mean to use the formal p-value approach, good. So let's do kind of a summary of chapter 5. You've already had it on the quiz, but of course it's going to come back to haunt us. All the things that you saw on the quiz, we're going to amp it up a little bit on quiz 3, right? Because it's going to reappear. So summary of chapter 5. Let's start with our conditions. And what I want to do is, if kind of space permits, I'm going to split it into a confidence interval and hypothesis testing, right? And so first, my conditions. Well, my first conditions that I have to check is independence. Which is going to be the same in both cases, right? Confidence intervals or hypothesis testing. So for independence, the sample must be randomly selected. And we usually say that's enough to be able to assume that we have independence. Remember, if it doesn't say the sample was randomly selected, then we have to assume that it was, right? So you have to state your assumptions. So here, maybe I'll say conditions / assumptions. Because I find that emphasizes more, right? That, okay, well, that's something that you're assuming then. Okay. So independence. So the sample must be randomly selected. And then the optional one, N has to be less than 10% of the population. Right, your sample size has to be less than 10%. of the entire population, right? And that goes back to, well, if I've collected too much of my population, then I'm going to introduce these dependent observations, right? And that's not good. Okay, so I had independence, and then I can't remember if I was calling it normality, but the normality condition is when we have to check our observed successes and failures or our expected successes and failures, right? So this is where we split into two groups, depending on if I'm going to do a confidence interval or a hypothesis test. So you'd have to read ahead and figure out what you have to do. Often you'll have to do both. So you'll have to check both. And if you have a null hypothesis, then there's no harm in checking both, right? But we need that null hypothesis. So independence and then normality. Now normality breaks up into two parts. If I'm doing a confidence interval versus a hypothesis test. In either case, we call it the success failure condition. Okay. So I'm going to break up my page here a little bit, and maybe I should not make that squiggle before I write anything, see if I have any room, but we'll try this. So the success failure condition for normality, if you're doing a confidence interval, is what? I have to have n times p hat has to be greater than or equal to 10, and n times q hat has to be greater than or equal to 10. These are my observed successes and failures, right? These are my observed successes and failures. Whereas if I'm doing a hypothesis test, really what I have to do is I have to skip ahead and figure out what my null hypothesis is, because I'm going to need to use my null value. Right, and so n times p naught, oops, clean that up. N times p naught has to be greater than 10, greater than or equal to 10, and n times q naught has to be greater than or equal to 10. So this is my expected successes and failures, given the null hypothesis that p is equal to p naught, right? So I go to my null hypothesis and I grab that null value and I check it against my sample size. Is my sample size large enough to detect those proportions that I'm hoping to be able to detect, right? That's what's going on there. Turns out my squiggly line was just fine. Okay. So once we have checked the conditions, and depending on what we're doing, right, we can either build a confidence interval or we can do a hypothesis test. I'm going to start with the confidence interval because it's nice and small. Okay. And maybe what I'll do is I'll kind of put pink boxes around things just to show the blocks. Okay, so if I have to do a confidence interval in general, my confidence interval is going to be what? It's going to be p hat plus minus some z star, oops, should be a star, times, and maybe I'll do this, bump it down, times the square root of p hat q hat over n. Where remember, this is the standard error of p hat, And let's see if I can find a different color here. And when we multiply it by that critical value, we get the margin of error of p hat, right? And z star is called a critical value. Right. Just kind of a summary of things that we need to know, right? Now, later today, when we calculate the sample size that we're going to need, we're going to refer back to this formula, right? Because what we're going to do is we're going to adjust based off of some desired margin of error. We can calculate what sample size we would need. Notice that we need the sample proportion, so that gets a little bit weird, right? Because how am I supposed to have a sample proportion if I haven't collected any data, right? I'm trying to decide how much data do I need. So it's kind of a catch-22. So I'll show you how to get around that. But for now, let's just focus on the interpretation. So the confidence interval, we have a standard blurb for our interpretation, which I hope that you used on your quiz. You'll get a chance to redeem yourself if you didn't, right? But the interpretation of the confidence interval is really important. So whenever we build a confidence interval, you're not just going to leave it at that. Your boss doesn't know what to do with that. So you have to interpret it for your boss. Okay, so the interpretation is that standard blurb. So we are some percentage, and by default, we have a 95% confidence interval. And that 95% confidence interval is related to the default alpha level of 0.05, right? And so we have a default alpha level of 0.05, which I can talk about now because we've seen it, right? And so, or I can build a confidence interval, a 95% confidence interval. And so here I'll say the 95% is the default. So we're 95% confident that the interval from blank, which is of course your lower value, whatever your lower value is, to blank, your upper value, captures, oops, doesn't look like captures the population proportion, right? And you would have to fill that in with whatever the population is, right? Captures blank which in our case is going to be the population proportion, right? The example that we had at one point when we were doing the confidence intervals was what proportion of Canadian adults have an RRSP, right? And so now we're talking about, okay, our 95% confidence interval, we're 95% confident that this interval, can't remember what it was, that's okay, captures the true population, of Canadian adults who have an RRSP, okay? So confidence intervals, everyone likes to do confidence intervals because once you get it and you have this interpretation kind of under your belt and you know what to do, then they're relatively easy, right? And so hypothesis testing, not so much, but once you get the hang of it, the steps, there's just a few more steps to do, but you'll find the same thing with the hypothesis testing with more practice. Okay, so for hypothesis testing, I break it up into 4 steps. But in this case, I'm not really going to break it up into steps because maybe you don't find that helpful. Although I do, I kind of rely on them a little bit. Maybe I'll outline them in orange here. So step 1 is to state your hypotheses. So here we have the null hypothesis is that P is equal to P naught. Now that's the case regardless. That's always going to be your null hypothesis. Okay. Your alternative hypothesis will depend on the question, right? So you could have an alternative hypothesis that P is not equal to P naught, right? Is there a difference? Has there been a change? Okay, so keywords like difference or change. Or if the question is asking is, and this is a 0, is this proportion significantly less than what we've seen in the past, or has there been a decrease, right? So then our alternative hypothesis, is that P is less than P naught. Okay, so if there's been a decrease, or if it's less than some value. And then finally, our last option is that P is greater than P naught. So from the question, you might have something mentioning, has there been an increase, a significant increase? And whenever we use the word significant, remember, we're talking about statistically significant. So do you have enough evidence to reject H naught, right? And H naught is up here and always up there the same until you have proof otherwise. And depending on what the question is, right, that's going to help put you towards your alternative hypothesis. So has there been an increase, or is it greater than some value? And this is where we also make a note of, do I have a two-sided test or a one-sided test, right? This doesn't come into play until step 3 when I have to find my p-value. And I know there's a lot of p's floating around and there's nothing that we can do about that, right? Here, these p's are in terms of the proportion, right? This is the proportion, so the population proportion for corresponding to my sample proportion. Oh, it's confusing, right? And then here's my null value, or my hypothesized proportion. So what did it used to be, right? And then my p-value is the probability of seeing something as extreme as what I saw, assuming that the null hypothesis is true, right? So there's kind of 3 p's. I'm sure there's more p's floating around, but those are the ones that are coming to mind. So for my p-value, right, if I'm concerned with either side, this is what we call a two-sided test. Two-sided test. It can also be a two-tailed test or two-tailed. But I call it a two-sided test or a one-sided test. And so these two, it doesn't matter which side it is, it's still going to be a one-sided test. So this is a one-sided test. I'll put step 2 on the next page here. Step 2 is to do the test, which for a one sample proportion means calculate a Z-score. And what's our Z-score going to be, right? So it means calculate the z-score. Z is p hat minus p naught over the square root of p naught q naught over n. Okay. Notice the change in the standard error, right? So slightly different because we're using the p naught q naught over n's, right? It's on that formula sheet that I posted, but I want you to have it here in front of you, right? So kind of summarized on a page. Okay. Since you're writing your quizzes and your final exam, oh my gosh, I almost forgot. The final exam date is posted and it is April 19th. And maybe I should scroll up and just kind of jot that down before I get carried away here. I'll bump this down and jot down that the final exam is April 19th from 9 to 12. And now that we have daylight savings, I think it's called PDT instead of PST, but I can't remember. But I am going to PST/PDT. We had daylight savings, so I don't, yeah, times have changed. And despite what it says on the final exam schedule, because I know there's going to be a lot of worries about it, it is going to be online. You'll be able to write it in that room with me, but there's another class in there as well, so kind of crowded, I think. So because so many of you are not here yet, we're going to do it online. And so it's going to be an online final exam. You'll have to be in our Zoom room. You'll have to have your cameras on, all that kind of fun stuff. I know, boring. And we'll talk more about that later. But it's on April 19th and it is online. Unless you want to be in person with me, then that's fine. But talk about nervous, right? And it is open book. Yeah. So this is different from the other sections, right? Because we have had this hybrid option, which kind of quickly turned online, but it got weird when everyone just wanted to be online anyways. So with this hybrid option, so if you're talking to people in another section, then it's not going to be the same. So we are online and they are in person, right? We have open book, they do not. All the list goes on. Okay. Okay. So, but it is open book, just like the quizzes. So you're going to do great. Okay. But we'll talk more about that obviously closer to. All right. So our z-score, we find how far is my sample proportion from my hypothesized proportion. If it's really far away, what does that mean? It means I have evidence against this value, right? This null hypothesized value, right? And so how can we translate that? Well, that's where the p-value comes in, right? How can I translate or kind of give a probability to how far away my sample proportion is from my hypothesized value? Just as a side note, Z is typically given to 2 decimal places if you're using the tables that I've posted. If you're using software, then it doesn't matter. And I think your assignments and your quizzes can handle both. Okay. So step 3 is to find the p-value. So now you're going to find the p-value depending on what what your alternative hypothesis is, right? So now I'm going to just snag this and copy this. And maybe I'll change the color of this because it's from earlier. Style, there. From step 1, okay, you're going to have one of these hypotheses, right? Alternative hypotheses. And if you have this alternative hypothesis, you have to find the area in one of the tails and then multiply it by 2 to replicate it in the other tail. Oops. Okay. So here it's centered on P naught, and then your Z is going to be in one of the tails, maybe over here, right? But then you have to replicate it down here. Find the area in one tail, then multiply it by 2 to find the two-sided p-value. I will say that there are lots of other ways, lots of other approaches that we could use. For example, what if I just said, okay, my alpha level is 0.05. What's the threshold, right? What Z score is going to be beyond that, right? That's what we call the critical value approach. So if you come across that, then that's totally fine. But I also don't want to confuse you with too many approaches that all do the same thing, because it's hard to make that connection initially, right? But you will start to see that there are other ways that we can do it as well. Okay. If your alternative hypothesis is that P is less than P naught, then your Z must be, your Z, and maybe I should do plus minus Z, because if your Z score is negative, then the positive side is actually the negative of Z. That's just me being picky, right? But if your Z score, then your Z must be negative, right? And then your one-sided p-value is going to be this area, right? This area in the tail, because you want to prove that it's the p-value is the probability of seeing something as extreme or more extreme than what you saw, right? And so here I'll make a note, calculated Z must be negative. Otherwise, what would you be testing? If you had a positive Z and you're trying to use it to prove that P is less than P naught, your p-value would actually be what? If you're trying to prove that P is less than P naught, but P ended up being larger than P naught, that doesn't make sense, right? But so then maybe you'd have a Z up here, and then this would be your p-value, which would be very large, right? So not enough evidence to reject H naught. There are a couple of those questions floating around where I get you to test a hypothesis that doesn't make sense using the data. So then you get a huge p-value, and that's okay, right? It's just then you don't have evidence to say that P is less than P naught. All right. And then finally, if my hypothesis is that P is greater than P naught, then hopefully my Z is above P naught. And then the probability of being as extreme or more extreme is, of course, in the upper tail. Okay. and here, right, must be positive. Just on the other side. Okay. Once you have your p-value, right? So regardless of if it's one-sided or two-sided, that is your p-value, right? So once you have your p-value, you're ready to draw your conclusion. Okay, so step 4 is your conclusion. Let me see how much room I have. Okay, got this much space until the end of my page. So I'm going to try to keep it on this page, because then it'll just be a total of how many pages long? 2.5-ish. It's not bad. Okay. So step 4, how have I been writing these, is your conclusion. Okay. Your conclusion has 3 parts, right? You compare your p-value to your alpha level. If it's less than the alpha level, then you have enough evidence to reject H0, right? If it's not, then you don't have enough evidence to reject H0. Okay, so step 1 is to compare your p-value to the alpha level. Then you're going to state your conclusion in terms of H0, in terms of H0. Then you're going to state your conclusion in terms of the question. Now, I can't believe I forgot to bring this up here. Let's see here. I need it. Here. Finally. That was worth the scroll. Because I can't believe I didn't have this before. I don't think I've shown it to you, but I know it's a little bit bad, but it also is really helpful for remembering what your conclusion is, right? So your conclusion in terms of your H0, if the P is low, so what's low? Well, less than the alpha level, right? Then the null hypothesis must go, right? So then you can reject H0 in favor of HA, okay? And so I know it's a little bit bad, but also the number of times that I've seen this scribbled kind of in the margins of final exams and stuff, I know that it's helpful. So so it's kind of catchy, right? Snoop. I guess Snoop's a grandpa now, so he might even be a great grandpa, who knows? But classic. So here, what this is saying is that if the p-value is less than the alpha level, we have enough evidence, skipped a word, to reject H0. Right? Whereas if the p-value is not, now I just like to negate it. So if the p-value is not less than the alpha level, we do not have enough evidence to reject H0. Versus if the p-value is not less than the alpha level, we do not have enough evidence to reject H0. Right, so here is not, then we do not have enough evidence to reject H0. Okay, I managed to keep it all on that one page, including my funny. So if you find it helpful, then that's great. If you don't, that's fine too. Okay, so your conclusion is always going to have the same pattern, right? So even though I know it feels like a lot right now, we're going to always use the same conclusion. So once you have your p-value, then your conclusion always follows this pattern, right? If it's less than the alpha level, then you have enough evidence to reject H0. And then, of course, what does that mean in terms of your question? Okay. So sample size calculations. So this is kind of the end of that little, I want to call it a one-pager. Maybe if I typed it up and made it a really small font, maybe it would be a one-pager, but it's not really. But kind of a summary of everything together, nothing that you don't need is in there, right? Sometimes I try to explain stuff as I go, but that can get confusing. So let's talk about sample size calculations. If we plan on conducting a one sample proportion hypothesis test, right, or a confidence interval, then we can calculate what sample size we would need. And maybe I want to start this in a different way. So before we collect a sample, we will often want to be able to calculate how large of a sample we'll need, right, to satisfy some criteria. So before we collect a sample, we often want to calculate the sample size we would need in order to satisfy some criteria. In order to satisfy some criteria. Oops. That criteria is going to be the confidence level, right? So the criteria is the confidence level. So the desired confidence level and also the desired and maybe what I'll do is I'll bump this over because I can and write desired in front. The desired confidence level as well as the desired margin of error. Okay. So one thing that I want you to note is that we will only do sample size calculations for one sample proportion questions. Okay. We will only consider sample size calculations for one sample proportion questions. Okay. So this is the only type of question where we're going to be able to do a sample size calculation. You can do it for one sample means, but it relies on some heavy assumptions that I don't like to make. And so So we're just going to do it in this one case. I can do it in other cases, but one is enough. Enough to check that box on your learning outcomes that we have to go through. So that's what's going on here. So we're only going to do the sample size calculation for one sample proportion questions. So if I have a confidence level, right? Remember, that sounds like a confidence interval, right? And I have some desired margin of error, then how we're going to do this is we're going to rely on where we get the margin of error from, which is the confidence interval, right? And so recall that p hat plus minus z star times p hat q hat over n. Remember that this is your margin of error. And z star is your critical value, which is how we communicate the confidence level, right? The critical value is how we communicate the confidence level to the confidence interval. Right? So, let's see here. So we've got some margin of error. And so remember, we're going to try to calculate the sample size we would need. So solve for n. So find n, right, in order to satisfy some criteria. So we have some desired confidence level. So I want to report a 99% confidence interval, right? And I have some desired margin of error. So I want my margin of error to be 0.01, for example, or 0.03 or 5%, which would be 0.05, right? So remember, we're talking about proportions. Proportions, remember, are between 0 and 1. So your margin of error is often quite small, right? 0.01 would be 1%. Okay. And so I don't need to write that down. I think you guys are okay with that. But your margin of error is often quite small. Okay. So if I have some margin of error, we can specify the confidence level by z star, and we can denote the desired margin of error by m, for example, right? You can use whatever variable you want, but I'm going to use m, and I'm pretty sure m is what I've used on your formula sheet. So it is on your formula sheet, but there's a couple of things I want to point out. So what that means is that I have m, which is the margin of error. So this is equal to z star times the square root of p hat q hat over n. So I can set those two equal to each other. And so is equal to z star times the square root of p hat q hat over n. And I want to try to solve for n. What's my first step then? Well, I need to get that square root on its own, right? And so don't worry, you're not going to have to derive this formula, but I do think it's really helpful to see it just once kind of work through. So if I want that square root on its own, then I would have to divide both sides by z star. So I get m over z star is the square root of p hat q hat over n. Now to get rid of that square root, right, I have to square both sides. And so I get m over z star squared is p hat q hat over n. I'm going to keep solving, even though I'm running into that problem that I mentioned before where, okay, well, I haven't collected a sample yet, so how on earth am I supposed to have a p hat, right? And we'll talk about, we have two options there, but let's just keep solving for n. So I find the easiest way to solve for n is to multiply it over and then divide this guy over here. So I do kind of a switcheroo here. So I get n times m over, oh, this is z star squared is equal to p hat q hat. So then if I am dividing by m over z star squared, now we can do this, right? I'll jot it down. I usually show way too much work, and not too much work, I just mean way more than most people do. And so if it's confusing to you, then that's okay. But really what you're doing, if you are just switching the numerator and the denominator when you're dividing it over, that's what's going to end up happening. But technically what you're doing is you're dividing by m over z star squared. M over z star squared, I can bring that square in if I want to by the exponent laws, but I'm going to keep it outside. But I do have a fraction over a fraction. So technically what you're doing is you're considering p hat q hat over 1, right? If I divide anything by 1, I can turn it into a fraction. So then I get n is p hat q hat over 1 divided by, and maybe I'll bring that square in for just a brief moment here, m squared over z squared, or z star squared. Now I have a fraction over a fraction. That's when I have to flip the denominator and multiply. Flip denominator and multiply. So what I get, and to match the formula sheet that I have, I'm going to put these guys in front. It doesn't matter if you're multiplying a times b or b times a, you get the same result. All right, so here I get z star squared over m squared times p hat q hat over n. By the exponent laws, I can extract that square if I don't want to have it on the individuals anymore. So then I get n is equal to z star over m squared. Oh, I don't know where I got this over n, that's just over 1. That's confusing, or that would have been confusing if you got rid of that. P hat q hat. The problem here is this is a problem since we haven't collected a sample yet. Since we haven't collected a sample yet. Okay. So we have two options. Okay. We can either use just a 50-50 split, and that's going to give us our most conservative estimate for the sample size calculation, right? So if you have no clue what's happening, then that's your best guess. Or if you have collected data in the past, then you can use that preliminary data. And so you can use that p hat from a previous sample as an estimate. Okay, so in general, N is going to be Z star over M squared times P star Q star. And that's on that formula sheet that I posted here. Let's see if I can kind of bring it so that it fits there. Okay. So here, notice that we've got the P star, Q star. Okay. We have two options for what we use for P star. Remember, Q star is just one minus P star. Okay. Note that, of course, Q star is just 1 minus P star. Okay, so we have two options for what we use as our P star. We have two options for what we use as our P star. Oops. P star, and then of course Q star is 1 minus P star. So we'll just talk about P star. Okay, option one is, so option one is the more conservative approach. Okay, so conservative approach. Let P star be 0.5. This will give us the largest possible value for N that we would need. Okay, so that's what makes it the most conservative approach. It also assumes that we have no knowledge, right? So this assumes we have no prior knowledge about the proportion, and it will give us the largest possible value of N, and will yield the largest possible value of N. Possible value of N we would need. And you can play around with the calculation. You can play around with 50-50 or 60-40 or 30-70. It doesn't matter which one's which, right? But what you'll find is that the value is maximized when, or the N is maximized when you have a 50-50 split. Okay. And so if, you know, money's no object, then you would usually just assume a 50-50 split. But what we're also going to find is that the sample sizes are, you know, relatively similar. The other option is to use preliminary data, right? And so use preliminary data approach. So if we have some prior knowledge, so a previous sample, for example, right, then we can use that sample proportion as our P star. So if we have prior knowledge, such as a previous sample, we can use that sample proportion as P star. So then Therefore, P star would be P hat from that previous proportion, or the previous sample rather. One important thing about your sample size calculation, and the last thing that I want to mention, is that because we're taking samples of people or animals or whatever, we can't take a portion of an observation, right? And so one thing here is note, got lots of notes today. Since we can't have a fraction or a portion, I'll say a portion of an observation, we always need to round up to the nearest whole number. We always need to round up to the nearest whole value to ensure that the margin of error is as small or smaller than what we wanted. To ensure the margin of error criteria is met. Because if you don't round up, if you round down, then your margin of error is going to be just a smidge larger than you wanted it to be, and that's bad, right? So to ensure the margin of error criteria is met. Oops. Okay, so you have to round up to the nearest whole value. So let's see here. When did we do? I think it was on March 8th, I want to say. We did a confidence interval, right? And we found that the margin of error was 0.029144. Okay. I'm going to copy this. From March 8th. And I also want to include I'm going to paste it as an image. I also want to include the question. Oh, what a messy question. How about this? So we had a sample proportion of 0.67, and we wanted to build a confidence interval. So we build a 95% confidence interval. So this is a 95% confidence interval. And what we found was that this was our margin of error. Okay. So now, what if I want to, and I've almost got these lines lined up. What if I want to, not quite, use this to calculate what sample size I would need. So this was done in 2012. And what if I want to do it now? Yikes, 10 years later, in 2022, right? So what if we want to conduct this study again? What if we want to conduct this study in 2022, oops, I almost put 2012 again, 2022, what sample size would we need? What sample size would we need? Right? Guess that's a question. Assume that we want to maintain the 95% confidence level. Assume we want to maintain the 95% confidence level. But want to decrease our margin of error. Maybe we want to be more precise, right? What does the margin of error do? The margin of error is what I think of as a buffer zone around my sample proportion, right? So what if I want to decrease that buffer zone and make my estimate more precise, right? Then I can decrease my margin of error to do that. And I want to decrease it to be, let's say, 0.02, right? Or maybe let's do 0.01 for something extreme. Assume we want to maintain the 95% confidence level and decrease the margin of error to 0.01, right? Which is the same as 1%, right? So my buffer is going to be 1%. Okay, so then I need to calculate my sample size. So remember, n is I just want to say here that let's do the calculation. So compare the conservative approach with the preliminary data approach. So compare the conservative approach, the conservative versus preliminary data approach. So the conservative approach uses P star is equal to 0.5. Good jumping off point. Whereas the preliminary data approach uses P star is equal to P hat, which in this case, P hat, right, is 0.67. So notice how there's a little bit of a shift here. Okay. So I need my N formula. So you have it on your formula sheet, or we can just jot it down again. So N, but I am running out of time, so I'm just going to copy this twice. So N and N. Okay. Z star is going to stay 1.96 because that's what I need for a 95% confidence interval. You would change that if you wanted to change the confidence level, but this is, so Z star is going to be 1.96. And you know what? I'm gonna just bump these down. Z star is 1.96 and Z star is 1.96. And I shouldn't have done such a bright color here. How about orange instead? And M, we're going to force it to be 0.01 in both cases. Right, so M is equal to 0.01 and this means Z star is 1.96. So in both of these cases, when I do my calculation, I have 1.96 over 0.01 squared times, and in this case, I have 0.5 times 0.5. Whereas in the preliminary data approach, I have the same information, 1.96 over 0.01 squared, but I use p hat instead of 0.5. So then I have 0.67 and 0.33, I want to say. Yeah. Needed my calculator anyways. Okay. So now my n calculation, and I find that it's just easier if you just go through and do it. So deal with the fractions first, then square it, then multiply by these p star q stars. So 1.96 divided by 0.01, and then square that times 0.5 times 0.5. Oh, darn, puts me at an even value of 9604. So no rounding necessary there, but I would have to round it if it wasn't even. 1.96 divided by 0.01 and then square it times 0.67 times 0.33, 8493.7776. And so n would have to be, I have to round up, right? So regardless of what the decimal is here, I have to round up, because if I just went to 8493, it would just, my margin of error would be slightly higher than I wanted it to be. So 8494. So if you compare these values, right, if you wanted to be really, really certain, so use that conservative approach, then you would have to find a slightly larger sample size. But once you're in these thousands, the difference between these two is not huge. So you may as well collect the full 9604 just to be on the safe side. Right. So good. So that's your sample size calculation, and that wraps up one sample proportion. So next day we're going to start 6.2 and talk about two sample proportions, and a lot of it is going to be just kind of similar to what we've already seen. So look forward to that. Anyways, if you have any questions, let me know. Otherwise, I hope you have a great day, and I'll see you on Thursday. Stop this. Thanks, guys.